Alright, back at another sample problem. This one is also from chapter 12. It's number 53. The problem reads, to what volume should you dilute 50.0 milliliters of a 5 molar potassium iodide solution such that 25 milliliters of the solution contains 3.05 grams of Ki? So this is sort of a hypothetical question, okay? And basically what it's telling us is we have a starting solution and then we're going to have a desired solution, okay? What are the characteristics of the starting solution? I like to draw a little picture to keep my mind wrapped around what's going on here, because otherwise it can get pretty confusing, okay? So to what volume should you dilute 50 milliliters? So I've got a beaker, and inside is 50 milliliters of a solution. That solution is 5 moles per liter, or 5 molar potassium iodide aqueous, okay? So that's my starting solution. And what this is basically asking me is I want to take the starting solution, and the key word is dilute. Dilute it, okay? I want to dilute it, which means to take it and add solvent such that it's less concentrated. Okay, so my desired solution characteristics are different, okay? What do I know about the desired solution? Well, they give me some characteristics of it. Specifically, that in my desired solution, for every 25 mils of that solution, I'm going to want that 25 milliliter volume to contain 3.05 grams of my solute potassium iodide, okay? So this is the sort of thing that we're faced with here, okay? Now, this is a pretty confusing problem because it's not typical that you would do this kind of thing in the lab. It's more of sort of an academic exercise, okay? But after thinking about it a couple minutes, I think we can develop a strategy. And ultimately the key word I think for our strategy is this, dilute, okay? We're going to perform a dilution, which means we're going to take this solution to make it less concentrated. And we're eventually going to make a solution with these characteristics, but we have to do it from this solution. We have to dilute this solution to make it happen, okay? So ultimately, we're going to come back to use what's referred to as the dilution equation. It's a pretty important equation for laboratory work in chemistry. You'll see a lot in your textbook, maybe on exams, and in the lab. And it goes something like this, okay? Says that the molarity in moles per liter of our stock solution times the volume of the stock solution used in the dilution has to be equal to the molarity of the diluted solution times the volume of the diluted solution. More generally, these molarity terms could be any concentration unit, and the volumes could be a variety of different volume units as long as you're consistent from one place to the next. But I like to use, whenever I can, molarity, moles per liter, and volume in liters. There's a very important reason for that. Because if you multiply molarity times volume, it's always going to equal the number of moles of solute if molarity is in moles per liter and volume is in liters. So moles per liter times liters always equals number of moles of solute. So this equation sometimes is kind of confusing to people, but it's really just a conservation of mass, conservation of number of moles type of equation. It's basically saying that when you make a dilution, the number of moles of the stock solution that you use ends up in your dilution. Okay, so it's kind of obvious if you think about it, but nonetheless, we're probably going to need to use that equation eventually. Now, what do we know about our desired solution? Here we call that the diluted solution. Okay. Well, we don't know the molarity. We actually don't know the final volume that we need to dilute this to. The conditions of the experiment specify that we have to dilute this to a larger volume to make a solution where this is true. Now, that doesn't mean that I need to get exactly 25 milliliters of the solution. In fact, I'll probably have more, but because we have to dilute at least 50, right? But this is a characteristic of this solution. Now, I look at this, and it's the amount of material of the solute per liter. And I think about that for a second, and I almost think, well, that's almost like a concentration, or it really is a concentration. It specifies amount of solute per volume of solution. So, could I convert that to, say, molarity, and then use this dilution equation to help me out? And that's really going to be my strategy here, okay? So what I'm going to do is I'm going to take my 3.05 grams of Ki. I feel like I need to get out of the way so y'all can see what I'm doing. So I'm taking my 3.05 grams of Ki. I'm going to convert that to moles. Do that by dividing by 166.0028 grams per mole. That's the molar mass of my potassium iodide. When I do the math on that, I have 0.018373 mole of Ki present in my hypothetical solution. Okay, so a little over 18 millimoles of Ki present in this solution, 0.0183 moles. Okay. Now again, it's a hypothetical solution, doesn't really exist, but I'm just trying to convert this measurement to a molarity. Okay, so it jives with the units over here ultimately. Right? Now, can I do that? Sure, because I now know that I've got this many moles Ki in my hypothetical solution. And if I divide that by my liters of volume, I can convert to a molarity that's representative of this hypothetical case. That's what I'm going to do. So I'm going to take my 25 milliliters that was specified. I'm going to divide it by 1,000 to express it in liters, which is 0.025 liters. So I have this many moles in this many liters. And of course I can do the division there. Quickly determine on my calculator the molarity of this desired solution is 0.73492 moles per liter. So what have I done? Just to rehash, okay? I know I have this as a starting material. The problem wants me to figure out how do I make this type of solution. Okay? I need to make a solution with a little over 3 grams per 25 mils. So what I decided to do was, instead of having this kind of awkward representation of a concentration, I'm going to convert it into a molarity. And that's what I did. I figured out how many moles of the solute, divided it by the liters of solution, and that's my molarity. Now the beauty of that is I now know the molarity of the diluted solution that I need to make. And I also know the characteristics of my stock solution. So I know my stock solution characteristics, I know my diluted solution characteristics, or at least starting to understand that a little bit better. So I can kind of take a step forward now and figure out exactly what I need to do from here. Okay? So now how in the world are we going to do that? Well, it seems to make sense that maybe we'll come back to this dilution equation, okay? The one that's right here. And I'm going to erase what I wrote below it, just because it's kind of in the way right now. I now know that the molarity of the solution that I want is 0.73492 moles per liter, or molar. Right? Everybody see that? Because we computed it before. Now, how am I going to make that solution? Well, the problem specified that I took this solution and I diluted it down. I diluted it down to whatever volume I need such that this condition could be met. Right? So it turns out that's my unknown then. The total volume of the diluted solution. I know I need this concentration, but remember, the problem specifies, and this is what makes this a little bit unusual, the problem specifies that I make the solution with this characteristic from the dilution of this stock material. I have to dilute this to make that. I have no other choice because that's how the problem reads, okay? So the question is how much do I need to dilute this down to make a solution with this characteristic, okay? So we decided already that this is the molarity of the desired solution. The volume is going to be our unknown. That's going to be the total volume that I need to dilute this down to, basically. So that's going to be what we're going to solve for. Now, what do I know about my stock solution? Well, I know it's 5 moles per liter, or 5 molar. Do I know the volume of it that I have to dilute? In liters, I do. And again, when I use this equation, I usually just change all my volumes to liters on purpose automatically at the beginning. I always like to use the dilution equation in terms of number of liters, because if you multiply again liters times moles per liter, you get mole units, and it just keeps everything organized for me, okay? So I almost always do that when I'm working on this type of business. So you've got one equation now, and this is a bracket, not a 1, if you're confused, okay? Sorry, it was a little bit sloppy down there at the bottom, okay? But we've got one equation with one variable. We can certainly solve that for V diluted. When we work out the math on that, works out to be about 0.34 liters, a little over 0.34 liters. Again, this is the number that just came off the calculator, okay? I haven't looked at the sig figs yet, and looking back to the beginning of the problem, it seems like our answer maybe, and this says 2, which kind of was important to go into things. I mean, I suppose we should truncate to 2, which would also be pretty easy. Just to round off there at that 0. Having our answer being 0.34 liters. Okay, so basically what this means is that if I want to make a solution with these characteristics, what I need to do is to take this 5 molar stock solution, which originally was 50 milliliters, and then I'm going to dilute it down to 0.34 liters. That's, of course, equivalent to 340 milliliters. So if I dilute this to 340 milliliters, I will have prepared a solution with these characteristics, okay? Did I prepare exactly 25 mils? No, because this was just a characteristic of the solution. It said that 25 milliliters of the solution contains 3.05 grams, okay? Doesn't mean I have to prepare exactly 25 milliliters from diluting this, which is impossible because you have to remove volume, not add it, right? And you can't simultaneously remove volume and decrease the concentration. You have to increase the volume to decrease the concentration. It's characteristic of a dilution, right? You have to add more solvent. So the problem itself reads a little bit confusing, but I think we've been able to reason our way through it. And hopefully going through this has been helpful for you. Sometimes the problems in the back of the chapter on the homework can be confusing just in the way they're worded and set up. To me, it's a little bit of a confusing read. And a key idea that you absolutely need to solve this type of problem is found right here in this dilution equation. Okay, that's kind of a fundamental piece of knowledge that the question is really meant and designed to test you about. Okay, so you have to know that to solve it, but you really have to kind of practice the problems a little bit to understand how it's written and where you have to go. Otherwise, it can be kind of frustrating. So don't get frustrated by that. Just kind of keep working at it, keep working these problems, and sooner or later, I think a light bulb will just kind of go on, and you'll understand what it's asking and what you need to do to find the answer. All right.